to be very happy to introduce today Zhengyi Zhou from the IAS, who will talk about hierarchies of contact manifolds via rational SFT.
Thank you for the introduction. So I will be talking about joint work with Augustine Moreno about hierarchies of contact manifold. All right. So yeah, okay. The slide is turned. So I will start with fundamental dichotomy of contact topology, which is a famous over-twisted versus tight. This is a phenomenon discovered by Algebraic in dimension 3 and Bowman-Algebraic-Murphy in higher dimensions. So roughly speaking, over-twisted contact manifold is a class of contact manifold where the existence and the uniqueness of contact structure is equivalent to the existence and uniqueness of underlying topological data, which is just a splitting of the tangent space into a trivial direction and a direction with almost contact structure, aka almost contact structure. And over-twist contact manifold shall be understood as the simplest contact manifold, where the contact information is essentially described by the topological information. So a natural question in contact topology is, can we classify contact manifold up to isomorphism? Well, if you are considering only over-twist contact manifold, the previous theorem basically says yes, if you can understand the topological question well enough. So basically means it's not a problem for symplectic geometers, I guess. And also there's many results in dimension 3 about classification of tight contact structures on certain manifold. But in general, this is a very hard question. So we're trying to ask a weaker question is, where can we understand the contact manifold up to cobordism? Since there is a great success of understanding cobordism in classical differential topology, unfortunately, this is also a very hard question, and I don't know the answer, but I will try to say something non-trivial about contact manifolds up to cobordism. All right, so I will first give the definition of cobordism I'm going to use in this talk, which is exact cobordism. From contact manifold y minus c minus to y plus c plus, if the symplectic manifold W has a boundary y minus y plus and has a one form lambda called the Liouville form, such that the exterior differential of the Liouville form is a symplectic form, and the Liouville vector field X, which is defined as the omega dual of the one form lambda, is pointing out along y plus and pointing in along y minus. And the compatibility condition is the contact structure on the boundary is given by the kernel of the restriction kernel of the Liouville form. Okay, and so my convention is the cobordism is always from the concave boundary to the convex boundary. Okay, so here we can have the natural definition of a category which called the exact symplectic cobordism category con, consists of contact manifolds as objects, and the morphisms are exact cobordisms. So the composition of morphisms will be the gluings of cobordisms. But strictly speaking, we can only glue cobordisms where the Liouville form restrict to the boundary where we glue are the same. So in general, we need to perturb things a little bit. So the actual definition should be morphisms are cobordisms up to homotopy, and then the composition is also like up to homotopy. Then we define the category. Okay. And the interesting feature about this category is it's not symmetric. That is, if you have a cobordism from A to B, it's not necessary there's a cobordism from B to A. So this is a huge difference compared to the usual cobordism category in differential topology. And roughly speaking, this puts a relation like a partial order to the collection of contact manifolds. And the principle, roughly speaking, is the complexity of contact manifold, contact topology is expected to increase in cobordism. So the convex boundary is typically like at least as same as complicated as the concave boundary. And we can kind of recast the basic dichotomy in contact topology that is, over-twisted contact manifolds are at the bottom of this order. So more precisely, in dimension 3, Antony and Honda proves that there exists exact cobordism from any over-twisted contact manifold to any contact manifold. And in higher dimensions, the same is also true if the topological obstruction vanishes. That is, we have, say, almost symplectic cobordism between the two contact manifolds. And the negative end is over-twisted, and we can make it exact cobordism. This is proved by Algebraic and Murphy. So the question is, can we get a hierarchy beyond tight is tighter than over-twisted? Okay. So the following structures can be considered as the geometric structures next to the over-twisted. That is something tighter than over-twisted. So we have the Giroux torsion in dimension 3, and the window generalized the Giroux torsion to planar K torsion in dimension 3. And in particular, planar 0 torsion is over-twisted, and the planar 1 torsion is Giroux torsion. And also we have the higher dimensional Giroux torsion introduced by method Niederkruger and Wendell. Okay, so we need to verify that these structures are tighter than over-twisted structures and understand like order among themselves, since we already see that here we have a number K, and hopefully this K will measure the complicity of the contact structure. So this is what we are trying to achieve. And a remark is having any of this geometric structure implies that the contact manifold is not strongly available. And since in this this hierarchy imposed by the contact cobordism exact symplectic cobordism category, things with fewer fillings are placed at the lower part. And if you have more filling, ideally you want to say the contact manifold is more complicated. All right. So the way to construct a hierarchy is following a composition like this. So we built a functor from the exact cobordism category con to some algebraic category, and then trying to build some functor from the algebraic category to a totally ordered set. That is, we are trying to deal with the problem from a field theory point of view. So one candidate field theory is a symplectic field theory introduced by Algebraic given Tauhofer back in 2000. And this theory also has many useful invariants. So there are a lot of possibilities we can explore here. So here is a quick recap of the SFT, which is we count holomorphic curves in the symplectization R times Y. Holomorphic curves with punctures asymptotic to real orbits at infinity. And then the SFT compactness implies that the boundary of the moduli spaces of curves behave like the following building breaking. So the T here stands for trivial cylinder. So in particular, if we count the rigid holomorphic curve and define some kind of structure maps by counting these curves, we will expect a quadratic relation among all these structure maps because the boundary always contains two non-trivial components, all others are trivial cylinders. So here is a prototype hierarchy called algebraic torsion. I will recall here. So first, we have a BV infinity formalism of the four SFTs. This is introduced by Chilibak and Lachev. So let V be the Q vector space spanned by the good real orbits of Y. So I'm gonna choose a non-direct contact form of Y. And we count all possible holomorphic curves. Then it will define as an operator called the SFT on this huge space that is power series in H with a coefficient in the symmetric algebra, which is it's a direct sum of the symmetrical product of V. And this DSFT is actually defined by, if I remember correctly, it's number of positive punctures plus genus minus 1. Wait a second. Sorry. So the SFT is Q minus, and the differential in Q plus, and the counting of holomorphic curves of genus G with positive puncture gamma plus and negative gamma minus. And there's also a correcting coefficient here. That's roughly how the operator looks like. So here we have a definition of algebraic torsion. ATY is defined to be the minimum number K such that H bar K is 0 in the homology of this huge chain complex. So in particular, we know that H bar K is always closed class. So this is asking for which K is actually an exact class. Okay, and the theorem due to Lachev and Wendell is this is actually a well-defined functor from contact exact cobordism category to the integers union infinity, and it's also surjective. And if this number is smaller than it's finite, then actually Y has no strong filling. And if Y is over twisted, then the algebraic torsion of Y is 0. So this also reflects that over twisted is sitting in the bottom of the hierarchy because it's mapped to the minimum element. And if Y has planar K torsion, then the algebraic torsion is at most K. So this is kind of a algebraic interpolation of the geometric concept of planar K torsion. All right, so let's move on to the general description of the algebraic structures of SFT. So the full SFT was originally packaged as wave algebra with a distinguished element H of odd grading, such that H star H is 0. However, there are some convenient reformulations, convenient in the sense that if you want to build a hierarchy functors, this algebra formula is more useful. So first one is a BV infinite algebra I just recalled due to Chilibek and Lachev. And another algebraic formula is due to Chilibek, Fukaya, Lachev, which is called IBL infinity algebra, stand for involutive by Lie infinity algebra. And the algebra formulas here essentially use the same class of holomorphic curves as before. The only difference is you want to go into the deepest level of operators and call that the basic structure of your algebra. And useful thing to keep in mind is that the IBO infinity relation is equivalent to the boundary configuration of SFT compactification. In other words, if you are considering holomorphic curves without any decoration, just the usual holomorphic curves in symplecticization, then the refinest algebraic structure you can get is IBM infinity algebra. Okay, and similarly, we have this similar story for rational SFT. So rational SFT is a specialization of SFT where we only consider rational curves. So this is originally packaged as a Poisson algebra with a distinguished element H of odd grading such that the bracket of H with itself is 0. They are also very useful reformulations of this algebra. So first we have a Q variable only rational SFT by Hierarchies. This actually appears in a blog series in Hierarchies blog post. And there are also the L infinity structures on contact homology introduced by Siegel. This is used in his definition of higher symplectic capacity. So here we would like to introduce another algebraic formalism, which is we call it BL infinity algebra, which stands for Bailey. So we take out the involutive. And as the name suggests, this is also this is specialization of the IBL infinity formalism. And the relation between this BL infinity algebra and the previous reformulation is kind of similar to the relation between IBL infinity and BV infinity. It's using the same class of holomorphic curves. It's just you go to the deepest level of the basic structures and call it's a structure and define things. Okay, so let's start with the actual definition of this BL infinity algebra. So a BL infinity algebra on a Z2 graded vector space V. So in this talk, our vector space will be a Q vector space. It's a family of operators PKL from the K symmetric tensor product V to the L symmetric tensor product V. Here the condition is K is always positive, but L can be 0. And all these operators will be assembled into a huge operator P hat from EV to EV itself. So here EV is just so this S bar is the reduced symmetric tensor product. So this is just we throw out the constant term. So this is SV, direct sum with S2 SV, direct sum is S3 SV, and all these things. So if you think of element in V is a character, SV is then element in SV is a word, but symmetric word, and S bar SV is actually a kind of a sentence. But this language is symmetric, so we don't care about the order. And the relation is this is differential, P hat differential, and the gradient is 1. To be more precise, it should be -1, but since we are using C2 grading, so I'm just using 1 here. So I need to explain how we actually assemble this P hat. So this P hat, the definition of the P hat is the following. So first we represent an element in SV by a little graph like this. So this will represent an element in S3V. And the top row here will represent an element in S bar SV. Okay, so in more precisely, this top row represents an element in S3V, symmetric tensor with S3V, symmetric tensor with S2V. And then we glue in a graph representing the operator PKL, that is a graph with K input and L output. And the rule of gluing is that we cannot create cycles. So in particular, this is bad. This will create cycle. And the remaining rule is for all these vertices here not get glued, I will add a dashed line, which stands for identity map. Then we have a glued graph, and the rule to determine the output is for each connected component of the glued graph will give me a component in S bar product, and each dot here will give me a component in V. So in particular, the output of this graph live in the space of S7V symmetric tensor with S2V. So here we have 7 dot and 2 dot here. And the definition of P hat is using a sum up all these possible graphs. Okay, that's a definition of BM algebra. So roughly speaking, any kind of quadratic relation you can always package it into a huge, I guess you can always package it into a huge chain complex, which is a differential 0. But the difference between A infinity, L infinity, BL infinity, IBL infinity is exactly what's the combinatorics of assemble the basic operators into a huge differential. That's kind of the difference. All right. Any questions about this algebra? Okay, let's move on. So if we use P hat 1 to denote a part of this P hat, which is using only operators with 1 input and any kind of output and on SV, that is P1 hat is the restriction of P hat on SV. Then you take the projection from EV to SV. This is a kind of the first component. S2 SV to the first component. Then this SV P hat 1 is a chain complex. And in the context of SFT, this is the context homology algebra. And if we similarly define the P hat K is a restriction of P hat on the SK SV. So it's a sentence with K words. And then we project use pi1 to the sentence with 1 word. Then we get actually a sequence of operators on SV. And this is actually a L infinity algebra. But if you want to to align this with the classical definition of L infinity algebra, you probably want to shift the degree by 1 of SV. And this is the L infinity algebra used in Siegel's higher symplectic capacities. And a BL infinity algebra, as I said, is a specialization of IBL infinity algebra. That is, if I have IBL infinity algebra, then I can get a BL infinity algebra. But the relation is not that direct, so we have to actually use equivalent reformulation of the original IBL infinity algebra. Then the relation will be most clear from there. But I will talk about this if I have time in the end. And the last thing is, as I said, that the BL infinity relation is precisely the boundary combinatorics of rational curves in simplifications. That is, this is a kind of refined structure you can get if you only consider the classical holomorphic curves without any decoration or any change, and using the SFT building compactification. All right. So next, we can define, kind of make a category out of this algebra. So, so a BL infinity morphism from a BL infinity algebra Vp to another BL infinity algebra V prime Q is a family of operators phi KL from the K symmetric tensor to the L symmetric tensor. The condition on KL is same as before. I can have L is 0, such that on the huge complex, the bar complex, we have induced map phi hat, which is called chain map, and the grading 0. And here's a phi hat is defined similarly, but now since we are mapping between different spaces, there's no sense to talk about identity maps. So the rule is you have to fear the second level with all possibilities of graphs representing phi KL. So every vertex has here has to glue to something, and the rule is also we cannot create any cycles. And the rule for the output is similar, that we count the connect component and count the bullet vertices inside the connect component to determine where does the output lie in. And so the figure here is something from S3V tensor S3V tensor S2V to S6V prime. But you can also have the configuration with disconnected graphs. It's okay. And the phi hat is the sum of all possibilities. All right. Okay. So inside this category of BL infinity algebras, there's actually a distinguished element which we call 0. And since the vector space is 0, so this operator PKL has to be 0. And this 0 is the initial object, meaning that we always have a morphism from 0 to V. And as usual, the structure map is forced to be 0 for like any integers. But on the other hand, 0 is not a terminal object. So we will call a BL infinity morphism from V to 0 a BL infinity augmentation. And if you unwrap the definition, it's basically a sequence of operators epsilon k from the K symmetrical tensor to the ground field Q satisfies the relation that epsilon hat composed with p hat is 0. Okay, so as I said, that 0 is not a terminal object. In fact, BL infinity augmentation does not always exist. So if I use the EKV to denote the truncation of this S bar SV, so this is inside S bar SV, I only take the symmetric tensor product, the first symmetric tensor product up to K. Then this P hat actually respects this filtration. This EKV is a filtration on the S bar, on the EV. And on the other hand, we know that for this 0 object, since P is 0, so the vector space EK0 is the same thing as the homology of this EK0. By the way, this EK0 is Q direct sum with Q direct sum with K copies of Q. Yeah. So I can use 1, 0 to denote the generator of the homology of E10, which is just a copy of Q. And also this 1, 0 is a class of the homology in EK0 for NAK. So now we can define the kind of the element 1V which is the image of 1, 0 under the induced map from EK0 to EKV, which is essentially just represented by the 1 in the first copy of Q in the SV. Okay, so here's a basic proposition is if 1V is 0 in the homology, then V has no BM augmentation. This is actually very easy to prove because if I have augmentation, so we always have 0 is the initial object, and we have augmentation here, then it will induce a map which is EKV0 to EKV to EK0, and this 1, 0 will send to 1V, but this 1, 0 also send to 1, 0 here, which is not 0. So if 1V is 0, then we get a contradiction of the existence of augmentation. So this proves the proposition. And given this, we can actually define a concept which is called the torsion of the BM algebra, which is defined to be the minimal number of k minus 1, such that this 1V is 0 in this homology. So if this torsion is smaller than infinity, then V has no augmentations, just from the proposition above. And another thing is this definition of torsion is actually a functor. That is, if we have a BM morphism from V to V prime, then we have the torsion TV is bigger or equal to TV prime. Okay, so this finished the discussion of obstructions to augmentations. So next, let's move on to the case where we do have augmentations. So suppose we have an augmentation epsilon, then we can construct another map, which I will call it F epsilon hat, which in some sense is identity plus epsilon hat. So what's the meaning of this? It's like I have a map, I have a sequence of operations that phi 1, 1 is identity, and phi k0 is epsilon k, and phi kl is 0 for any other coefficient. And by the same rule, it will define me a kind of a phi hat from EV to EV, following the same rule we use to define BMVT morphisms. Of course, this is not a self-morphism. I'm just building a map. And similarly, we can define the other guy, which is kind of the hat version of identity minus epsilon. The property of these things is they are actually inverse to each other. So we can actually use this as a change of coordinates, which is basically like this. We have the original p hat, and we can use a change of coordinate, which is f epsilon hat and f epsilon hat. And then we can get to induce the p epsilon hat. And the basic property is just from the commuted square, I know that p epsilon hat square is 0. And another thing is actually p epsilon hat is assembled similarly from a sequence of operations p epsilon kl using the same pattern of how you assemble p hat. Okay, but the additional property we have is the p epsilon k0 is 0 for any k. So we eliminate all the constant term basically. And here is a picture of how you assemble a p epsilon kl. Okay, so maybe this is not a proper name, like call it a linearization, because I'm not taking out just a linear term. I'm just eliminate the constant term. But I don't know what's a better word, and it's kind of what people usually call, like, used to define linearized contact homology, things like that. It's just trying to eliminate constant term. All right. So next is another algebraic definition, which we call the point map. So a point map on a BL infinity algebra VP is a family of operators P dot KL from SKV to SLV, such that the P dot hat is a chain morphism with certain degree. Okay, and the P dot hat is assembled from P dot KL by the same rule as P hat. That is, on the second level, you're only gluing one operator representing this P dot. So although the algebraic relation is again chain morphism, but this P dot cannot be understood as a BFT morphism. because the combinatorics is more like a differential rather than morphism. And in practice, this P dot KL will arise from moduli spaces in symplectization with one mark point subject to a constraint. That is, the constraint can be a closed singular chain in the contact manifold Y with possibly local tangency conditions. But in the definition of our geometric invariant, the constraint will always be just one point. So we are counting holomorphic curves passing through one fixed point in Y. Okay, and given augmentation epsilon, we can similarly define kind of the change of coordinates that of P dot epsilon hat and satisfy relations that same relation. And again, this P dot epsilon hat is also assembled from a sequence of operators P dot epsilon KL by that similar graph defined in the previous slide. But it's no longer true that this P dot epsilon K0 is 0 anymore. And the abstraction of this operator being not 0 is on the homological level. It's the second hierarchy that we want to define. So here is a definition of the second hierarchy, which we call the order of the augmentation epsilon and P dot. And this is the minimum number of K such that 1 is the image of this map. So let me explain what is this going on. So so first of all, we know that PK 0 epsilon is 0. So that will imply that V PK1 epsilon, this guy is an infinity algebra. Once you eliminate the constant term, we get the infinity algebra just by taking a small portion of this B infinity algebra. And then we can talk about the bar complex, which is, so this L hat epsilon is a differential on bar complex. And this B bar KV is a truncation of bar complex, which I only take the symmetric tensor product of the first K component. And this L hat dot epsilon is just a direct sum of the map we are interested in. Sorry, there should be no hat here. That is this. And indeed, that this L hat dot epsilon is a chain map from this homology to Q. Sorry, from this chain complex to Q. So the property is I want to find the minimum K such that this map is non-trivial. That is also saying that there's some non-trivial non-trivial thing in this guy. Okay, so this is the definition of this order. All right, and we also kind of want to define a kind of a category of these things. So given a B infinity morphism phi, such that each V and V prime are equipped with point maps P dot and Q dot, there's notion of compatibility, which is just a family of operators phi dot KL, and that will assemble you a huge operator phi hat dot and satisfy certain homotopy relations, basically. And in practice, this phi dot KL will count holomorphic curves with one mark point subject to a constraint, which is some cobordism, subject to a cobordism constraint in the symplectic cobordism. And in our case, since we only consider point constraints, the constraint for phi dot will typically be a path in the cobordism connecting the 2 points at the positive infinity and negative infinity. That's how the geometry construction of these things. And the basic algebra property of this is if we know that phi, P dot, Q dot are compatible, then we know the order of V. Then we know that for any augmentation epsilon of V prime, then epsilon composed with V is the augmentation of V. And when we use this augmentation for V, we know that the order of V will be bigger or equal to the order of V prime using augmentation epsilon. That's kind of a functorial property of this definition of order. And then we can get rid of the augmentation just by like enumerate all possible augmentations. So we can define the order of the P dot as the maximum of all possible augmentations for like all possible, the maximum of the order for all possible augmentations. So in particular, if there's no augmentation, then this is defined to be 0. Okay, and the consequence of proposition above is if we know that P dot Q dot phi are compatible, then we know the order of V P dot is bigger than order of V prime Q dot. Okay. So now I have finished all the algebraic preparation of the invariant. So now we can move on to the actual symplectic geometry. So this will be an application of SFT. As you know that there's serious transversality issues in building an SFT. So in our case, we have to also use some virtual techniques to get transversality for all holomorphic curves. So here is a theorem we need to construct our invariant. So let Y be a contact manifold with a non-generic contact form alpha. Then there exists a set of non-empty set of auxiliary data theta, such that for every auxiliary data, there we have a B infinity algebra P theta on V alpha, where V alpha is a vector space generated by good revolve orbits of alpha. And this P theta is actually, for example, defined as coefficient of P. So this is so coefficient of this operation is defined to be some correction term and the number of holomorphic curves with gamma epsilon as a positive asymptotics and gamma minus as a negative asymptotics. We have to, this is the definition. So morally what we need is define this virtual count. And so in the actual proof of this theorem, you have to choose your favorite virtual techniques that will actually define what's the meaning of this set of auxiliary data. It depends on the choice. And the next thing we need is also for the situation for the cobordism, which is if we have a strict exact cobordism from Y prime alpha prime to Y alpha. So strict means that the cobordism which has a Liouville form lambda, then lambda restrict to Y is alpha, and lambda restrict to Y prime is alpha prime. That's what I mean by strict. Then for the sets of auxiliary data for alpha and alpha prime, we have another set of auxiliary data C, capital C, for the cobordism, for the BFT morphism, and the surjective map from the auxiliary data of C to the product of auxiliary data, such that for every C, so for every auxiliary data for the cobordism, we have a BFT morphism from the induced BFT algebras on the boundary, where this theta and theta prime is the image of the auxiliary data under this projection. Okay, and the third property is kind of tautological. It says for every compatible, so for every auxiliary data theta, there exists a compatible, just auxiliary data k theta, such that for the scaled contact form, such that the pk theta is identified with p theta by the canonical identification of the reorbits of alpha and k alpha. Because for the, after you rescale the contact form, the geometric setup for the curve counting is exactly the same. So you should expect this. So this is more or less tautological, but turns out this is a kind of useful property we need. And we also have similar statement for point maps. But I have to point out here that we didn't construct the rational SFT as BMT algebra. this is actually a minimum, very minimum requirement from virtual techniques. You cannot say the PU-infinity algebra associated to the contact manifold is kind of well defined just from this. So the key thing is we actually didn't talk about compositions and homotopy equivalence at all. Okay, and the homotopy equivalence in SFT is a quite subtle subject, both in algebraic formalism and also in curve counting definitions. Okay, so to avoid the construction, the theorem above be completely trivial. That is P theta KL is 0 and the phi CKL is 0 for all. This is kind of a condition where the previous theorem is satisfied. To avoid this, we need the following, I think, which deserve to be called an axiom for virtual techniques. So a virtual implementation of a holomorphic curve theory has a property that the virtual count of a compactified moduli space equals to the geometric count when the transversality holds for that moduli space. And this is a bridge connecting a general construction of invariant and how you use an invariant to like say something geometric. Because in general, we cannot get a classical transversality for all curves, but in some preferable cases, we can get the transversality for the curve we are interested in. Then we're trying to use computation from there. Okay, and to prove the previous theorem of virtual techniques, we use Pardon's VFC package for contact homology algebra. And it's important to note that the combinatorics for rational SFT is essentially like very similar to the contact homology algebra because it's tree-like, there's no cycle there. It's just it's not a canonically rooted tree. So I guess the only tiny difference between these two formalism is the gluing parameter space is slightly different. You have to prove that thing is for rational SFT is again stratified. But of course, any other construction of the symplectic field theory, i.e. using polyfold or Krunischi structures will also suffice to provide the virtual techniques. So the whole point is the virtual techniques requirement for our invariants is really kind of minimum. Okay, and for this axiom, which is also important, is also satisfied in Pardon's construction, and it's kind of nice there is Pardon's perturbation in some sense infinitesimal. So this axiom satisfied for any choice of auxiliary data. But for perturbative methods like polyfold or Krunischi structures, this axiom holds if you choose your perturbation small enough. But in any case, this axiom is indeed satisfied for any virtual techniques. Okay, so now we are ready to define our invariant, finally define it. So for a contact manifold Y, we define the algebraic planar torsion of this contact manifold to be the torsion of the PU-infinity algebra using any non-degenerate contact form alpha and any auxiliary data theta. And similarly, we can define the planarity of Y, which is defined to be the order of this PU-infinity algebra. And but you have to take the maximum over all possible augmentations and all possible points. So this is counting curves with point constraint. Oh, and this is kind of a set of auxiliary data for the pointing map. Just you take all the possibility, take the maximum. And the claim is that both of them are well-defined functors from exact cobordism category count to integer union infinity. So here is a quick proof of why it's well-defined. So if I have y, alpha, and theta, and I have another choice of contact form alpha prime, and another choice of auxiliary data theta prime, but we have we can build a cobordism where here is alpha prime, here is kind of 1 over k alpha, here is a contact form is k alpha. We can build an exact cobordism like this, and we can use 1 over k theta as auxiliary data here, and k theta as auxiliary data here. and this is the auxiliary data theta is here. So that will imply that TV alpha theta is bigger or equal to TV alpha prime theta prime, and bigger or equal to TV alpha theta again, because the rescale doesn't change the algebra. Okay, so it sounds like tautological proof, but what's going on actually is because we are not building the rational SFT as functor from exact cobordism category to the B infinity algebra category up to homotopy, we are building something to a totally ordered set, where in the totally ordered set, there's no ambiguity about composed to morphisms. As long as it's composable, it's unique. And there's also no ambiguity of homotopy equivalence because among two objects, there exists a unique morphism. So that's why we can get rid of the discussion of all these things. Yeah, so the point is like the composition is well defined, but the first functor is not. Okay, and of course, so far, you can if we don't have the axioms that we can count geometrically, if the manifold, if the moduli space cut off transversely, you can possibly assign all PKL as 0. Then the algebraic planar torsion and the planarity T will always be infinity. There's no structure at all. But with the axiom, this is actually interesting invariance. Okay, and there is another kind of refined structure when the planarity is 1. And this is not from the like the Euro algebraic formula that you can get from the B infinity algebra. It's something very special for SFT. That is, in the planarity is 1, that is 1 is in the image of this map on the restrict to the homology of VP epsilon 1, 1. But in the SFT context, this homology is a linearized contact homology, which carries the modular QU modular structure. This is the cohomology of the classified space of S1, because we have S1 action basically. And this group as a QU modular is actually torsion. So every element will essentially killed by multiply U. And this structure is discovered by Bourgeois and Wanscher. And so now we can define a kind of a refinement in the case of PY is 1. That is, we take out the element in this homology such that it will be mapped to 1 by this P dot epsilon. And then we keep track of what's the minimum number of K such that it's killed by this U map. And then we take the maximum of this for all possible points and augmentations. Then we kind of get another functor from exact cobordism category to integers. And by formally define this order of semi-dilation as infinity if Py is bigger than 1, and defined to be 0 when Py is 0, then SD is another well-defined functor from the exact cobordism category to integer union infinity. Okay, so now comes to our main theorem, which is if we assemble all these functors together, we get a covariant monoidal functor. That is, we call it hierarchy of contact complicity from the exact cobordism category to H. H is a totally ordered set, like the displayed in the below. So the first piece here is where the planarity is 0. So the Py will be 0. Now recall that this is equivalent to that there's no augmentation. So Py, so planarity 0 is equivalent to there's no B infinity augmentation. So that in this case, if I have finite algebraic planarity is kind of a refinement of this hierarchy. So we have this, all these were corresponding to like you have some finite, this is APTY where equals to 1. Okay, and the second level is when the planarity is 1. And then we have a refinement of this order semi-dilation. In this case, we have another integer refinement. And all these are when the planarity is bigger than 1. And it's very possible that we can have refinement for each piece of it, but we haven't do that yet. Okay, and in fact, this functor is surjective except 2 elements, which is this and this. So we don't know except these two elements, we know that everything in this total order set corresponding to some contact manifold. Okay, and this guy, APT, this element corresponding to P is 0, but APT is infinity. That is no augmentation, but no finite torsion. Okay, so algebraically, you can actually construct a BFT algebra satisfies this condition that there's no augmentation, also no finite torsion. One thing you can use is, say, since we are working over Q, you can use Q is not algebraic closed, because augmentation is essentially solving some algebraic equation, and you can try to make the solution is not in Q, then you can find an example like this. But the question, potentially there are also other abstractions, even you are working with algebraic closed field. But the question is really, suppose you have an example like this, how can you construct a contact manifold satisfy the condition? And this infinite SD is kind of, you have a sequence of augmentations such that the order of semi-dilation will blow up. But we also don't know any example satisfies this condition, but it's a reasonable possibility. Okay, and the monoid structure here is the monoid structure on the exact Boolean category is given by the disjoint union, and the monoid structure on H is more involved. But the point is you can compute disjoint unions from each component. Okay. All right. So it's a quite non-trivial question to ask whether different choices of virtual techniques give rise to the same functor HCX. But the good news is, since we're assuming the axiom that if we can count things when it's cut out transversely, the following properties of the functor is independent of the virtual techniques you choose. So the functor have the following properties. So first, if Y has planar K torsion, then the algebraic planar torsion of Y is also smaller than K, just like algebraic torsion. Of course, the proof of this is essentially the same as what Lachev and Wendell did. And if Y is over twisted, then APT Y is 0. So again, that over twisted manifold is mapped to the minimum object in this totally ordered set. And if Y has a higher dimensional Giroux torsion than APTY is smaller or equal to 1. And if APTY is smaller than infinity, then Y is not strongly fillable, just like the algebraic torsion. And if Y admits the exact filling, then the planarity will always be bigger or equal to 1. Okay, and next, if Y is iterate open book, that is, you can find a kind of open book decomposition of Y. So Y equals to open book of page and monodromy, and this you find the Lefschetz fibration. And you keep doing the Lefschetz fibration for the fiber, and until on the very end you get if you get a planar page, that is you kind of starting this fibration construction starting with a planar surface that is called iterate planar open book, and the initial page has K punctures, then the planarity is smaller or equal to K. And another thing is, if Y has the exact filling that is not K unit ruled, so K unit ruled is that there exists a universal upper bound lambda bigger than 0, that there exists a holomorphic curve pass through any point P with area smaller than epsilon, smaller than lambda, and at most K punctures. So this is the definition of symplectic K unit ruled introduced by MacLean. So if you have the exact filling is not K unit ruled, then we know the planarity of the contact boundary will be at least K plus 1. So we have upper bound and lower bound. And the last thing is,
I have a quick question.
Yes.
Did you mean to say genus 0 in that definition just now?
Genus 0. Oh, yes, yes, that's correct. So the curve has to be rational curve. Yes, thank you. Yes. And the last property is we know that APT, SD, P are all surjective. In particular, P is surjective in all dimension bigger than 3. So APT is surjective in dimension 3. This is essentially the result by larger than window. And in high dimensions, we know the image is non-trivial. They cover something, not just one element. And for SD, we know that the image, the size of the image will increase with respect to dimension, but we don't know, like in each dimension, whether it's surjective. Because as the name suggests that this semi-dilation is related to the definition of K dilation or K semi-dilation I introduced in a paper last year. And the example is essentially the same. So the point is you're trying to show, like when you enumerate over all possible augmentations, the computation is still correct. And the planarity is fortunately surjective in all dimensions. And the point is kind of planarity is something like easier to compute in some sense. APT requires some holomorphic curve, actually very hard to find in high dimensions. But planarity, the challenge for planarity or order of semi-dilation is you have to enumerate over all augmentations. Sometimes will be annoying, but just for the curve concern, it's usually easier to find. All right. Yeah, I guess this is kind of a good place to stop. Also, I have like maybe 10 pages of slides about applications, computations, and the comparison between BA infinity and IBA infinity, and the relation of algebraic planar torsion and algebraic torsion. But I guess this is a good place to stop for questions.
Thank you very much. So indeed, if there are questions, please go ahead.
I'm trying to think of a way to make this question more specific, but basically I would like to hear something about the relationship between algebraic planar torsion and algebraic torsion.
Okay, yeah, so that's at the very end. Okay, so relation to IBA infinity algebras. Sorry, there will be more algebras. It's sorry about that. So, so let me first introduce the definition for IBA infinity algebra, which is it's a family of operators, PKLG, from SKV to SLV. Again, the condition is K is positive, but G and L can be 0. So G will be the genus, L will be number of output, and they will be assembled into a big element, a big operator P hat. So this guy is S bar SV adjoint with H, or more precisely, it will be SV adjoint with H, a direct sum with a symmetric tensor product. So it's SV tensor over the, but over tensor over this coefficient along Q, and maybe make it symmetric. That's the definition of this EV H bar. And the picture is again similar, as you have a similar picture description, but the rule now is you can actually create cycles here. That's allowed. And you have a decoration G here to kind of thinking of there's like small surface here with genus G. And the rule is again, same as the output, every component of the output will give you element in the S bar component, and every dot will give you component in V. So this picture shows something from S3V, symmetric tensor S3V, symmetric tensor S3V to H1 plus G, S6V, symmetric tensor S2V, because here you have genus G, here you create one more genus. So this is the BFD relation. IBF, so the relation is this is square to 0. Okay. Okay. So if you look at this, it's slightly different from the original IB infinity algebra introduced by Chilibak, Fukaya, and Lachev. So it's actually equivalent to the formalism when they have another variable which is tau, keep track of all the class. But in this case, we have to set it into 1. And so you can see that actually they are equivalent. One easy direction is if you take a p hat, restrict to the first component, and take the pi 1 of it, then this is exactly the operator you defined in the original Chilibak-Fukaya-Lachev formalism. And this guy being square root to 0 is their IB affinity relation. So easy direction is that the definition in the previous slides where implies Chilibak-Fukaya-Lachev. But on the other hand, you can show that this Chilibak-Fukaya-Lachev will imply the previous one also. Yeah. So the algebraic torsion is kind of defined on this level. So on this level.
Do you know examples where the two invariants differ?
I don't. Like algebraically, I think it's possible, but geometrically, we don't know if there's examples that are different. But there's one example in Augustine's thesis with genus 1 thing. But the computation is not quite complete, but it's very likely that we provide something with low algebraic torsion, but higher algebraic planar torsion.
If I recall, that's a situation where you have some higher genus curve that comes from string topology.
Yeah, I think so. Yeah. Yeah. So, anyways, this is formalism will give you that IB infinity algebra will induce the PK L0 will actually be infinity algebra. So they're actually like a genus filtration. You can take in the EV H bar. You can consider kind of the tensor with the QH such that you tensor with a torsion. And when you take this guy is just H bar to the 1, then you can recover kind of B infinity algebra. Yeah, so from this we can have kind of a lot of torsions. You can define a lot of torsions. That is, we say IB infinity has an NM torsion if H bar to the n is 0 in the homology of this guy with the bar complex contains at most n+1. So the algebraic torsion is 0 n0 torsion, and you can use kind of the genus filtration to define another torsion which we call NMK torsion. That is, if H bar to the n is 0 in this with genus filtration up to k, then the algebraic planar torsion is 0 n 0 torsion, just algebraically, and the relation is, well, you don't need to read this. The relation is if you have 0 n torsion, then imply a n0 torsion, and also imply 0 n 0 torsion. And what actually you proved with Yanko is if Y admits a planar K torsion, then the full SFT has a 0K torsion, like the strongest torsion. That will imply both torsions. But as far as just from the algebra, we don't know if there's a direct relation between the algebraic torsion and algebraic planar torsion. So the difference is kind of like you make different requirement on what's the possible curves that will contribute to your torsions and what's the closeness requirement you make, like how many curves you have to exclude, and so how many curves you have to include. That's kind of a relation. So this is kind of explain the difference between these three torsions. And you can define similar structures for planarities, but I guess it's very hard to like actually make it a useful geometric concept because higher genus curve is very hard to find. So, but algebraically, it's always possible to define something.
Right.
Okay, any more questions? So I had one, so you mentioned at some moment that you had some computations.
Yes.
You skipped over, so maybe you just give us a little idea what.
Yes. I guess one interesting computation is this, because remember that we talk about that if we have a filling that is not uniruled, then the planarity is kind of bounded below. So the natural class you look is kind of boundaries with uniruled fillings. So the natural case is you look at the F1 varieties in CPN. So if you take a divisor, which is k generic hyperplanes in CPN for n bigger or equal to 2, then we do the computation for the planarity of the boundary. So when k is smaller than n, this hierarchy functor is 0 SD, but this is subcritical. This DC is T star T maybe n minus k plus 1 times some copy of k minus 1, I guess. Maybe I messed up the quotient, but anyway, it's subcritical. And when the number is k is equal to n plus 1, this is you remove all the toric divisors, and so this DC is T star Tn. And the contact boundary is planarity is 2. And when you in the general case that if k is bigger than n plus 1, we know the planarity is at least the k plus 1 minus n. But in this region, that if k is bigger than n plus 1 but smaller than 3n minus 1 over 2, then the planarity is exactly this. This n being old condition is really technical. One should drop this. If one work harder with the virtual techniques, but we want to make things simple, so this is there. But it's actually interesting to look at this upper bound. So I guess this upper bound is definitely not optimal, but existence of upper bound is potentially necessary because in the definition of planarity, you have to enumerate over all augmentations. That's sometimes problematic, and so here is an example that if you take the dAs, which is a smooth degree k hypersurface in CPN, so the degree is high enough, and then the planarity of the boundary is infinity. So the thing here is if you use the augmentation from ds, from the complement of ds, just using the FM variety in CPN, the planarity will be finite. And it's actually, the planarity will always be k plus 1 minus n. But the point is you have some weird augmentation, which might not coming from an actual filling, but this guy become infinity. So that potentially suggests that some kind of upper bound here is necessary. So the point is you're trying to show something, some behavior persists without the influence from augmentation. And the similar results will hold for like final hypersurfaces in CPN plus 1. The point is you use the holomorphic curve there and trying to argue that it will contribute non-trivially to your environment.
So P equals infinity implies that the contact manifold is not iterated planar, right?
Yeah.
In those examples, do you know of any other way to prove that it's not iterated planar?
No.
Okay.
So there's a actually quite nice application is in all dimension bigger than 5 and NA contact almost contact manifold, which has a representative which is exactly fillable. Then in the same almost contact structure, there's a contact structure that is not iterated planar. So there exists a lot.
Interesting.
Yeah. So it's actually interesting is although the iterated planar give you upper bound, but in many cases the upper bound is not optimal. It seems like the good place to look for this invariant is inside these F1 varieties. And a scientific approach to compute this should be like derive a formula using relative Gromov-Witten or log Gromov-Witten, doing something similar to Diago and Lisi did for simplex homology. That will be more scientific. But for our case, we really use like the most simple curve in CPN and try to compute things. In general, we should expect some kind of formula relating to Gromov-Witten. Yeah. And maybe it's actually, I think it's a good place to mention this problem. I think it's quite natural. Is in general, if you take a very ample line bundle over smooth for project Friday, and for every holomorphic section of the line bundle, you take out this zero set, which the divisor will always be affine Friday. And the slides, yes. And the projective space of the holomorphic sections will be stratified by the singularity type of the divisor. And the top stratum will corresponding to the divisor smooth with multiplicity 1. Although this is quite hard because in general, we don't have a classification of the singularity types, but just pretend we can do that. And the stratification is governed by a category. Ideally, it will be a poset. It's a morphism from strata A to strata B is if we can change the singularity type of the zero set from A to B by arbitrarily small perturbation. That is, A is contained in the closure of B. So this will give us another thing is we get exact embedding from XS to XS prime, where S prime is a perturbed section. So this gave us kind of natural functors from category of strata to the exact cobordism category or the under category, which is objects are Liouville domains and the morphism are embeddings. So the natural question is like how rigid are those functors? Like is it kind of injective embedding into our exact cobordism categories? So the previous series says something about the cobordism. There's like some part is very rigid. But if you care about the embedding, it's actually there are more things like you can say. So here's a theorem that is, if you take out the K hyperplanes, then after K is bigger than N, then this guy cannot embed into with smaller hyperplanes. But dkc is always embedded into dk plus 1c exactly. The natural conclusion is a symplectic, but the issue is not exact. So the abstraction is not topological. And this result is obtained independently by Gnatra and Siegel. And we posted the paper the same day. And but they discuss more general configurations. Like they talk about the divisor can be higher degree hypersurfaces, normal crossing. We only talk about hyperplanes. Yeah. So invariant you can use is for example, it's just defines the order of semi-dilation or order of planarity on Liouville domains. That is using the augmentation from the filling, not enumerate over all possible augmentations. So computationally, this will be easier to carry out. But conceptually, the funny thing is conceptually, it will be harder to define because if you want to define this rational, this invariant, you kind of need to talk about homotopy, which is hard. And in fact, the homotopy discussed in Pardon's construction is not good enough for this discussion. So it's kind of a trade-off. Yeah, and they define more general things like they consider point mass with point constraint with tangent conditions. And in particular, there's one particular tangent condition where zero invariant is very, very easy to compute. Yeah, but for our proof, actually, we didn't use the invariant for SFT. We use this invariant. I think it should be credited to MacLean. That is the order of unirootedness. That is exact domain is defined as the order of uniroot is like a minimum number of k such that it's k uniroot. And the theorem is, of course, this is a functor. This is proven by MacLean. And the theorem is the order uniroot of the divisor complement is increasing after k is bigger than n, then get obstruction. So the question is, I think it's a kind of natural question is, are the geometric invariants and algebraic invariants always the same? Which is the case for this divisor complement. Yeah.
All right, so let's see if there are any other questions. So if not, let's thank Zhengyi again. Thank you very much for your